So that's the old-fashioned way of thinking. That's how all these papers are done. Now you're so much smarter than back because you know you're supposed to do it on a lattice. So actually what you have to do is you have to compare me and my two neighbors every place. So, you have a different formulation, and the equation of motion is saying, equation of motion has two parts. There's Laplacian. Laplacian is comparison with the neighbors.
Yeah.
And then there is what happens here, in Atlanta, not in Las Vegas. That's the nonlinear map is defined there. And I have to make sure that, the weight of these two guys versus my thing and possibly some translation term, in the potential, they all add up to zero. They have to balance each other.
Yeah.
So we solve it that way, and we always solve it globally. We always solve it by looking at orbit stability matrix rather than stepping forward in time. And stepping forward in time is just ugly. The stupid unknown map is, it's asymmetric. You don't see that the thing has symmetry when you look at it. It's this fake field and polynomial. You look at the function as it goes forward, and it's just something that has a couple coefficients, etc. It's not very pretty. But on the lattice, it's amazing. It just says, I do my thing, and then I look at my two neighbors, and they say, you're too tall, you're too short, whatever. Do it again. And everybody has to do it because we're all democratically equal on a chain. And that's what, some method like Newton method or Wattai method or Biham and Menzel method or Lan and Sutanovich method, some other method will do. It will change everybody's height in such a way that the thing is harmonious. Everybody is in balance with the neighbors. And in that case, you don't think past the future, you just think of your neighbors. For this system, there's even no difference between them because you can't tell the difference between left and right. That's a convention.
My question is, if I'm going to try and find these periodic orbits, right? You're saying give an initial guess, see like how much it moves away, like to the left or to the right of the of the orbit, right? So my initial guess, do I have to give an initial guess for the entire lattice at once? So I have to give a guess for what the value is at each lattice point and then start iterating.
Yeah, and that's what I keep telling you. That's why I'm telling you about these M's.
Yeah.
That's their role. So let me now share my figure. This is for Bernoulli map, and I haven't figured out how to do it in a pretty way. So here is my very unsuccessful figure. I really think of all these problems as landscapes. Okay, so here is how I think you would do it for Bernoulli. On the left axis, lattice site, 0, 1, 2, 3, 4. People stuck in Newtonian way of thinking think this is time. 0, 1 minute, 2 minutes, 3, 4 minutes. On the horizontal axis is my landscape. And the way it works is that, there are three valleys. There is a valley and a peak, and then valley and a peak, valley and a peak. And if you look at it, this is Bernoulli map of slab 4. If you just look at given instant in time. So that's, my world. It consists of 4 valleys. But central committee sends me instructions. They're these M's. So it says, hey, you better be in a valley 3 when you get started. And it says, well, you got to be in valley 2 next time. Stay in valley 2. Then go to valley 0, then go to valley. So I get a string of instructions. So now I make a kind of lousy itinerary, lousy guess how I'm going to do this. And what I say is that every one of these valleys has a fixed point. So, this is a fixed point. There's a fixed point there. If I just draw a diagonal at my instant, I'll get periodic points for this problem. Every valley has only one fixed point. And everybody who is my neighbor is qualitatively the same. Everybody stretches with the slope in my neighborhood. So then I say, well, let me, as a first guess, say that my orbit is I go from this fixed point to that fixed point to that stay, that fixed point, etc. And this is my first guess what my trajectory or my lattice state is supposed to look like. Now, the problem is this lattice state is every place wrong, because when I compare where I am with my Laplacian term, comparing it to neighbors, it turns out every place it violates the condition that called my Euler-Lagrange equation. I have now a trajectory which is a wrong trajectory in terms of where it's really supposed to be, but it's correct in terms of topology. It's visiting the right regions. But I'm violating this law. Locally, this is being violated because my previous point stretched by factor s compared to where I'm now is not precisely this integer, but it's some other number. So that's not working. So then I improve the whole guess by moving all these points simultaneously using any algorithm like Newton iteration, which will change n points, but get you closer to the fixed point in the n-dimensional space. Now, what will happen in your case, the valleys will be bent, In your case, what will happen is instead of having this landscape with 4 valleys, I'll have one peak, then I'll go down and I'll have a bottom and I'll go up again. So I'll have qualitatively 3 kinds. I have a left side of the mountain, I have the slope between the 2 mountains, and I have a right side of the mountain. So that's what the cubic will look like. But it'll be the same idea. I would get myself using translations, which are now real number, not values are not integers. This is really measured in field values. I would make a bad guess, but which is topologically correct, but wrong in a detail. Then satisfy the equation, which is the one that you have. Your equation is given by orbit Jacobian for each sequence and the sources.
Okay. So
imagine this will be very robust for you. Any method will solve this problem because topology is so robust. The 3 regions are so distinct from each other. You won't be able to screw it up.
And there should be a fixed point for each kind of
We know that that's an obvious theorem about Smale horseshoes, is that as I give you longer instruction sequence, then the region that has that instruction sequence is shrinking exponentially, because every time you go step in time, what used to be a region of this horseshoe gets divided into 3 different regions, well separated, all of them thinner. As I go forward in time, these things shrink to 0. So the limit is, and periodic orbit is just repeated infinitely. So when you can realize every itinerary, then the limit will always be a point. So you will always know that there is a solution. And it's especially easy when this is a periodic itinerary, because you just have to solve it for one period and then it'll be correct forever after. Guaranteed to work. Don't worry right now about if stretching is not sufficiently strong. Let's just understand this case where you have a very nice horseshoe. Everybody's separate and clean. Let's do that guy first.
So my initial guess doesn't have to satisfy the sort of
No, the initial can be as stupid as you want, but it just has to hop against correct regions. So your initial guess says, I can't see all the details. So really there are 3 regions, left, center, and right. I'll take any good representative of 3 regions. Now, mathematics says every region has a shortest periodic point in it. So use that. That's well defined. One step, every one of these regions has a fixed point. So let me use that fixed point as representative for the whole region, for the behavior. And it's not quite good because the region is bending. It's nonlinear manifold. So the other neighbors are slightly different, but qualitatively they're doing the same thing. They're stretching and shrinking the same way I am. but slightly different, but topologically it has the same character. While the guy next to me is totally different because the other region flips. It's topologically not only that it's has a different stretching grade, but the guys that used to be left and right, now they're right to the left because flipping changes the order of things. So it's very different region. So in which region you are. So you can use this very coarse partitioning to get your guesses. Now, when you get smart, then I know that all the regions are of the size 1/3⁹, so they're small regions. Then I should use that knowledge to make a guess for the next one. In that case, you'll be very good in guessing next one because you're using numbers which are specified to 8 digits already or something. And they don't have much variation because they're very, very tightly bound in the small counter set parts, many levels of counter set down, so they're very tightly bound. You will use that to compute the ones which are one step further away, and they'll be very quick. And so on. So eventually you'll have a machine that'll just produce as many orbits as you want for these low dimensional problems. If you're doing fluid dynamics, it might be hard because embedding state space is very large dimensional, but in these problems, it's going to be very simple. This time it becomes applied, it's optimization problem. Put some kind of rubber band describing qualitatively what you want to do, but then you have to make it, obey the traffic laws at every spot. And that's, the equation that you have.
Okay. So any type of optimization problem should work for this.
At the beginning, then at some point you get incredibly smart. At some point you realize that Matt Goodorf has already done all this. So you will learn how to use Orbit Hunter because he has gone this way, over 4 or 5 years of his research. Not on a discretized lattice, but on discretization, which is Fourier discretization of continuum of fluid dynamics. But the spirit is quite similar. And what's a big deal about all this is that you do not ever evolve forward in time.
Yeah.
Or you do not have to evolve in space in some way. And that's a great blessing because these are very unstable problems. But what you're doing is very stable. If you have this rubber band, you cannot destroy it. You can do some stupid step in Newton routine that maybe deforms it and gives you a different itinerary, different solution. But it's kind of hard to do because locally you would have to move it long distance to do the wrong thing, and that's probably not going to happen.
And so for the length of lattices that I guess, do I only have to give a guess that's as long as the period I'm trying to find? So if I'm trying to find it.
That's it. No, that's wonderful. That's what's nice about these compact solutions. So the ergodic solutions, the solutions which go every place, if you give them infinite time to wander around. And mathematicians love them and they can prove theorems, but for us they're useless because they're uncontrollable usually. We do not know how to get handle on them. The compact solution, so the d-dimensional tori that we use here, very nice. There are very few of them when the torus is small. Prime orbits for phi cube. There are 2 fixed points, 1 period, 2 periods, 3. There are very few of them for short periods. And their number eventually grows, but they get to be exponentially better and better cover of state space. So there is some balance there where you don't need to compute long ones unless you need some insane accuracy for some reason, but usually you don't. The thing is very robust.
Yeah, so I'm trying to think about how I'm gonna do this computation. So I'll just make a array of m values, and that array is my instructions, where I want.
Yeah, that's an instruction set. And if I'm correct, and if it's done correctly, what it does is it says in every one of these coarse neighborhoods, left, center, right, I have a separate dynamical system, separate map. For this neighborhood, I use this thing. And I don't care that this is part of a cubic or quintic or whatever. I just need to know how it works in this neighborhood. This is only part of my function I need to use. Other neighborhood, I use a different map. It could be really different. It could be a different part of the same complicated map. What I need to do, my instruction set has to put me into that neighborhood so I can apply that map. So that's instruction set. It's a set of translations. Each one of them, centering you in the right place so you can apply that map. You start this, it's exact for periodic points, but it's not exact for anything else because all the other cycles are away from periodic points. All unstable states tend to push their neighbors away, so they're away. But qualitatively, they're doing the same thing. They're stretching within some bounds in the same way. Then the exact solution, which you'll find by, I think, optimization or variation, exact solution only topologically obeys what central committee told it. But it doesn't go exactly. It's, if you go from Atlanta to New York, you don't go from Centennial Park to the Times Square. You just go to the city, they go to the region, right? All the time obeying the traffic laws. You're not allowed to discontinuously jump from this road to that road. You have to smoothly drive to it. And that's guaranteed by these local conditions. This local condition says, I'm not allowed to, my Laplacian cannot give me a very large number, meaning local curvature, because that means I would, drive a very tight turn or curve, which I'm not allowed to do because that's costly. So that's what the local stuff does. And optimization says, let me make sure that every place along my road, I correct for my errors. My map gave me this continuous instruction, I make it more and more smooth and continuous. The way to do this is to do this globally. For example, I'm trying to go to Uranus. And the problem going to Uranus, I get kicked around a lot by various planets. So I could try to aim my rocket with precision of 10 to the minus 24 angstroms or something in some angle in such a way that I shoot it and it just goes, and it hits Uranus. But that's now not how the engineering of it works. It'll go to some Lagrange point and I'll give it a little boost. So I'll choose the right direction. They'll go to some other point and I'll get slung along. And all the time, I'll be listening to these instructions, these M's, and choosing the right thing along the way. And that works. But there is no way to start here, shoot the rocket and hit something far away. Just like playing billiards or throwing a boomerang. You can throw a boomerang a little bit, but you can't throw it arbitrarily complicated way and make it come back. It just can't be done because it's exponentially unstable and nobody can beat exponentials. The exponentials cannot be beat.
In here, because this is like a Bernoulli map, the M's are all integer values.
Yeah, they just happen to be, and we like integers. And now you will have some letter which will have discrete value, L, C, R, or maybe 0, 1, 2, or minus 1, 0, 1. But they will be only labels. They will just say, now I have to move 2.73 to the left, which is a calculation that's specific to this problem for specific parameters. But topologically, I'll say, well, there are three options, but execution of them requires a particular setup, particular parameter values and particular system.
So I should make the M's the values of the 3 fixed point for just a one cycle, right?
I'm suggesting that will work.
Okay.
Now you might find out that you might start using M's which depend on 2 or 3 points, on the neighborhoods to get more precise things.
Okay.
which is saying, I will be partitioning space not in the 3 neighborhood, but maybe 9 neighborhoods, which is described by all period 2 orbits and repeats of the fixed points I have. So that in practice, you might find that you will go that way. You use the information you already have to get much better guess what to do next. What's baffling about this landscape, it's an ugly landscape because it has this precipitous sides, right? Bernoulli map goes up, then boom, drops. But the picture that Shankar will produce will be a very nice, mountain going up, going to the valley and going up again. So what looks like these little jagged teeth here will be a landscape that makes sense, right? And that landscape you have at every instant in time. That's your function. That's your phi cube function of phi-4 theory. As you go discretely in time, you will either stay in the valley or the same mountainside, or you will be asked to cross over. And that'll be easier to draw a picture and maybe to draw a nice mathematical or something shaded picture where you see a mountainside. It's not these sharp things that are confusing. And then it just says we are looking at little rubber bands that wander around and eventually come back because you're looking at periodic ones, but in a way that is agreeing with the motion, where the left-hand side is now going to be orbit Jacobian matrix multiplying. Well, you know what it is. I mean, it's a local stretching on this side and compare its 2 neighbors in a case. It's very simple. And this M will come in to make sure that the solution you're looking at is one of those values. So maybe that picture will be easier for people to understand. Topologically, you know what you want to do. You want to go to the kitchen, back to the bedroom, kitchen, bathroom. You have an itinerary.
Yeah.
And now you just try to make it the shortest and least painful walk between all these rooms.